Okay, so in today's preview, I will start from derivatives. So we have talked about continuities because if a function is continuous, then it will give some good properties like the preserving of compactness and something like Weierstrass theorem. But sometimes we need a stronger condition or a stronger properties to help us. So we define the differentiable function. The function from AB to R is differentiable at x if the limit exists and equals L. So, and in this case, we say the derivatives of f at x is f prime x equals F. So this is the definition of differentiable at x. So what is this term means? This means if we have a function and here is our point x, and t is any point like this, then this term gives you the slope of x and t. So as t is closer to x, and you will be closer and closer to the tangent line, the slope of the tangent line of x. Or whether it is approach from the left side or right side, it must converge to the same limits. Okay, a function f is differentiable if it is differentiable at all x in the open interval AB. Okay, let's see some examples. So if fx equals x squared, what is the derivatives? So we calculate the definition is equals s squared minus t squared of limits s squared minus t squared x minus t equals limit x plus t. So this equals to x. So we have f prime x equals to x. So fx is differentiable everywhere. Is differentiable. Next one, sine x is differentiable. So this means we need to compute sine x minus sine t divided by x minus t. Okay, so sine x minus sine t equals 2 cosine. I write down. 2 cosine x plus t over 2 Does anyone remember this formula? Maybe in senior high school.
Actually, that's something very interesting because so you learn that formula in senior high school, but you never know why. What on earth is that for? But it's actually for this calculation. But you never know that. you just memorize all that in high school.
So this will equal to x minus t divided by 2 cosine 2x plus t and sine 2x minus t. So this term equals 1 because limits of sine theta divided by theta is 1. So this equals 1. So this will equal to cosine x. So sine x is differentiable and f prime x equals cosine x. Okay, x1. The absolute value of x is not differentiable at 0. Again, we calculate the limits. Oh, this is 0. So this is t. So this equals limits t absolute value of t. This limit does not exist because if we approach from left side, this negative side, this equals -1. But if we approach from the right side, it will equals to 1. So this limit does not exist. Okay, so the absolute value of x is not differentiable. So if we draw the diagram, we can see at 0 because it is the point here is too sharp. So we can't find a tangent line at here. So this gives you a sense that a differentiable function must be smooth enough. Okay, first proposition, differentiable implies continuity. So we say differentiable is a stronger condition than the continuity. Okay, why? Because limits exist. This limit exists, so as x minus t close to 0, fx and ft is close enough. Otherwise, this term will explode and the limit does not exist. So this gives you the continuity. Okay. The converse is not true. Continuity does not imply differentiable because we have this function. This function is continuous but not differentiable at 0. If f differentiable is f prime continuous, is this true? Can anyone give some counter example of this one? Oh, and we asked that f prime must exist. So this is not a counter example because it does not exist at 0. Nobody? Okay, I'll give take fx equals s squared sine 1 over x when x does not equal to 0, and 0 when x equals 0. So we have shown that this function is.
Sorry, I have a question about why differentiability implies continuity.
Because when x
Yeah.
minus t is close to 0,
Yeah.
this must be close to 0.
Oh, because it exists.
Yes.
Okay.
So we have shown this function is continuous.
I think the most straightforward way is to see that you can see f(x minus f of t) equals to x minus t times x minus f of x t. So we know this one goes to 0, but this one goes to some L, so this one goes to 0.
So because this function is continuous, and we can calculate its differential derivatives, and it will equals to 2x sine 1 over x minus cosine 1 over x when x is not 0, and at 0 it is 0. The diagram of x squared sine x is like like this. So it will at 0 the derivative is 0, but the graph of this is something like this. Okay, so the function of the f prime x shakes up and down intensively near x, near 0. So this function is not continuous. Next, we prove some common properties of derivatives. First, f plus g prime equals f prime plus g prime. Second one, fg prime equals f prime g plus fg prime. Third, the constant, if f equals constant, then f prime is 0. And that's one. The derivatives of f over g is g squared f prime g minus f g prime. Okay, we just prove this by definition. The limits of to x fx plus gx minus ft minus gt x minus t equals limits t to x fx minus ft x minus t plus g of x minus g of t x minus t. So this equal to f prime x plus g prime x. Second one. The limits of fg fx g of x minus ft gt divided by x minus t is equal to, we're adding a term of minus fx gt, then we add it back. Minus ft gt. So this equals to fx times g of x minus g of t, x minus t, plus ft or g of t, f of x minus ft, x minus t. So it equals to fx g of prime x plus f prime x g of x. Okay, number 3. Okay, the third part is very easy because limit c minus c x minus t is 0 because it is constant everywhere. Okay, the last part, we can divide f over f into 2 parts, which is f times 1 over g. So if we can calculate this one, then after using the second properties, we will obtain the f over f derivative. So to calculate the derivative of 1 over g, this is tough. First we have this equals 0 because this is a constant 1. So by the third properties and the second properties, these equal to g prime dot 1 over g plus g dot 1 over g prime, and implies 1 over g prime equals negative g squared g prime. Okay, then we use the second property. F over g prime equals f prime times 1 over g plus f times negative g prime g squared, and this equals to g squared f prime g minus f g prime. Let us calculate the derivative of s squared again using the multiplication property. Then f prime equals x derivatives times x plus x times x prime, which equals to x. And the derivatives of x cubic is x2 prime times x plus x2 times x prime, which equals 3x squared. So by induction, using induction, you can show that xn prime is equal to nxn minus 1. Good one. Fx equals sine x over x. Then f prime x equals x squared, then sine x prime times x minus sine x times x prime. So this x does not equals to 0. So we have shown that sine x, the differential derivatives of sine x is cosine x. So this equals x squared cosine x times x minus sine x when x is not 0. Is that okay? Okay, now we show some good properties that differential.
So do we know that x prime is 1?
Oh, that's easy because x minus t divided by x minus t limits is
Yeah.
1.
Yeah, but I mean that's something that we need to know.
Okay. Okay, the first important theorem is the Rolle's theorem. It says that if f is differentiable and fa equals fb, then there exists c in AB such that f prime a or f prime c equals 0. Okay, so first we consider the most simplest case. If f is constant, then for all x in AB, f prime x equals 0. If not, recall the Weierstrass theorem, which says that because AB closed interval is compact in R, so it achieves maximum or and minimum in the interval by Weierstrass theorem. F achieves
double S.
oh
Weierstrass.
Weierstrass. Yes.
A-U?
A
Strauss.
I think it's stress.
Weierstrass.
Achieves maximum or minimum in the middle because f is not constant. Okay, so suppose FC is maximum without loss of general relativity. And C is in AB. Okay, so what's F prime C? F prime C equals the limits of FC minus FT minus d. And this should be equal 0. Why? Because fc minus ft is always larger than 0. This term is always larger or equals 0, but this term can be positive or negative, since we can approach from the left side or right side. So this limit, if it exists, it must equal 0. Okay. So this c is what we want. So in fact, both if a function attains its local maximum, then here and here the derivatives must be 0. And same is for minimum. If fc is minimum, you can see that this term is always negative. So again, this must be 0. Okay, now we are ready to prove one of the most important theorem about derivatives, the mean value theorem. It says that if f is differentiable, then there exists C in AB such that FB minus FA is equal to F prime C B minus A. So Rolle's theorem is a special case of mean value theorem, because when FB equals FA, this term is 0 or not. Oh yes. Okay. We will use Rolle's theorem to prove the mean value theorem. But FB is not necessarily equals FA. So we want to construct a function that is differentiable and with GB equals GA. So we consider a function something like this. And that R equals the slope between A and B. Okay, by doing this, we can show GB minus GA equals FB minus FA minus R times B minus A. So this will be 0. So GB equals GA. Okay, now we can use the Rolle's theorem. By Rolle's theorem, there exists C in AB such that G prime C equals F prime X minus R is 0. So this implies F prime C is equals R equals FB FA minus FA divided by B minus A, which is what we want. So this proves the mean value theorem. an easy proposition. If f prime x is larger than 0 for all x, then f is increasing. Or strictly increasing. Because fb minus fa, if b is larger than a, is equal to x prime c b minus a for some c in the interval ab, which is larger than 0 because f prime c by assumption is 0 and b is larger than a. So fb must strictly larger than a. So that's a easy application of mean value theorem. Okay, I think we're done. I'm going too fast.
Like, you can do some graphical interpretation here.
Yeah.
Oh, yes.
Can I ask? Yeah, because I don't think I understand Rose theorem. Maybe I'm way too away from the. Yeah. So f prime. Yeah. So why is f prime minus why is fc minus ft equal to 0?
Because from the left side, if we approach c from the left side, this term must larger than 0. So you obtain, because this term is positive, if this term is positive or equal to 0, you have the derivative must larger or equal to 0. If we approach from the right side, this term is negative, but this term is positive or equals 0. So we obtain the limits must smaller than.
Oh, I see. So you're talking about the left limit and the right limit.
Yes.
So maybe you should write all of that down.
Okay, so before I do that, I draw diagram for the mean value theorem.
Okay. Yeah, because.
Okay. The mean value theorem
Skipping
says that. Oh, I forgot to draw it. If this is the slope between A and B, if f is differentiable, you can find some points between A and B such that the slope of the tangent line is the same with the slope between A and B.
So you can see that why we need this, why we define this, because we're trying to find this point, right? And we're somehow like having to find this point. It seems like we need to let it back, something like this. So it's like somehow like the training in economics. We're doing this training and want to like eliminate this kind of training. And so this point, it seems like it's this point here. Right. So what's this? It's G. So the rho, you're applying rho on G, you're searching for this point. And it's equivalent to search for this point. This is the intuition behind this proof. And this is like similar. When you see this, you get a positive slope, and we go to the another side, we got a negative slope. So in limit, it must be 0.
Any questions? Okay, I think the
Yeah,
theory is
it's
over.
Bye bye.
We are looking.
但是拜拜，但是拜拜，
拜拜。
拜拜，拜拜。好。